present. Um, this is a little bit of a loose end, and this is the last topic we'll get to before galaxies, where we know a lot about star forming, and there are these extra little bits of matter that are the refuse of the star-forming cloud, but we actually care about them a lot. So as far as the whole mass energy budget of the universe, totally unimportant, but for us, really important. So we'll start with our galaxy on Wednesday, and more presentations, awesome. So we basically have all of the details that at least are currently known in place. We know how to make a star with a protostellar or protoplanetary disk, two names for the same thing. And we know about the jet, we know about all the details, and now we want to talk about the little bits of stuff that may coalesce out of them. And this is a topic that would have been very highly speculative, wouldn't have even been in the curriculum like 15 years ago, so much has been learned since then. And the second thing we're going to do is, essentially outside of parallax, our universe has been 2D. So the celestial sphere idea of just like stuff painted on this sky globe, it was difficult to get away from. Finally, we figured out parallax, and we found distances to close stars. But now we want to get out to like 10 billion light years, and the way to do it is Doppler shift. So it's really going to add depth to the universe and be something that we'll use beyond just doing some exoplanet detection. And then finally, a little bit of statistics of what we know about planets in the Milky Way galaxy, at least. We'll get to that on Wednesday. So this we have the whole chronological story, and now hopefully you guys are even comfortable playing that story out of a star's life and death in the abstract 7-dimensional luminosity, temperature, radius, color, spectral type, mass space of the HR diagram. So a big cold cloud of gas spins out into a cloud, collapses, burns for its main sequence lifetime, and then in two groups, the high mass group and the low mass group, freaks out and leaves behind a remnant and a cloud of some type. So great. And I'll show these just because talking about them is one thing, but to get a little bit of scale on this picture, I ran into a couple of pretty recent simulations about this whole process beyond these highly cartoonified pictures. So this is basically what happens when you teach the laws of physics to, I think we want to do the other one first, sorry. When you teach the laws of physics to a computer and then you leave the room for, whatever, a couple of months to a year. And this first one is a giant cloud of molecular gas. So it just happened to be circular, but the workers perturbed it a little bit. So giant cold cloud of gas, 500 solar masses, maybe like 12 light years across. And what's this going to end up as? Couple of solar systems, one solar system, something like that. Get a picture in your head of what you think this is going to end up at the end of this very fast-paced, maybe 100,000 years of evolution. Okay, got it? Okay. So again, this is like initial cloud of 500 times the mass of the sun. It's maybe at 30 degrees above absolute zero. And then just going to bump it and let gravity go. And this happens a lot in simulations, is all of a sudden the person has to, we're rotating and zooming. But the code needs to come in and kind of say like, oh, you've hit critical density. We're going to turn you into a star. So in fact, all of these things flying off are mostly brown dwarfs, like 2 of 3 of them are dwarf stars. But this is, when you look at, like, for instance, the Pillars of Creation, that Hubble image from Orion's belt, this is the snapshot that you're seeing. And this is the process, that very violent, cataclysmic process that you're actually getting a glimpse into. And what's not depicted is all the dust that obscures telescopic observations, which is a giant pain in the ass. So what am I going to have at the end of this collapse is I'm going to have a cluster of stars. And some get thrown way out. We were one of those. some remain inside and live out their entire cluster lives. And we're grateful for them because we can do what you guys just finished doing, is figure out properties of stellar lifetimes through CMDs. So that's the big picture. And just realize that we talked about it kind of very specifically for one particular star, but this is happening on a broad scale. Yeah. The gravitational slingshot. So these things fly out because they have a close encounter with another very heavy body. So it's the same way that we got, the Voyager and Pioneer probes to go really, really fast. We had them slingshot around Jupiter, and Jupiter gave them a gravity assist. This is the same thing, but these are like entire solar systems getting gravity slingshotted around. So that one just got ejected because it had a close encounter with another, heavier star probably. So, yeah, and this is what happened during late heavy bombardment within our own solar system. So the question is, what percentage of stars collide? You mean like bang on collision where they rip each other apart? Yeah, so the clouds will interact, but remember the grapefruit model. So I told we'll use it twice today, actually. What's the distance in between grapefruit sun here in Seattle and the tangerine that is Alpha Centauri? So in the grapefruit model, sun's about this big, and the nearest star to us would be about the size of a tangerine in New York City. So even under these extreme conditions of, 4 times, 10 times the number of stars in the same volume, well, what we're really talking about is taking, like half a dozen more citrus fruit and putting them in between here and New York. So it really, the idea of 2 stars colliding, like, pools on a pool table, is almost vanishingly small. So when you see these things slingshotting around each other, what you're really seeing is they're interacting by their gravity only, and there's no... Even when we collide with the Andromeda Galaxy, there will be very few things that you would call like a stellar collision. So, yeah, it's not bumper cars. It's more like gravitational kind of whiplashing and slingshotting. Other questions? Okay, now zoom in on one of those bright little dots, and you get something that looks like this. So within that, there's a cloud of gas with a central star, which is not indicated, and then you get these gravitational instabilities, and then you get planet formation. So this is just the laws of physics taught to a computer, and you get, you start seeing some chunks form, and then if you follow one of these chunks, maybe it interacts with another chunk and gets chucked out. So again, gravitational slingshotting. Possibly frames. So this is somebody's actual science, where this is grams per centimeter cubed. And remember how many grams per centimeter cubed Earth is? Like 5 or so. This is 10 to the minus 5 at the high end of the scale. So this is like very, very diffuse gas. I think this is just the frame number. So they propagate forward in time in discrete steps. So propagate the bits of gas, sometime take a step, download the data. So I think it just frames. Yeah, these are a little bit unfinished, but they're borderline on state-of-the-art. So that's what's going on. At this point, it seems very clear to us, for very many reasons, the answer to this question. Generically speaking, do other stars have planets? Yeah. Not too long ago, people were burned at the stake for saying yes to that. So it's worth just kind of mentioning that this is, we have the luxury through, a lot of new science and computer modeling to not be impressed by this. But this really was like a very huge, kind of iconic question in human existence, and whether or not we're the only planet out there and what these things were. It occupied humanity for maybe even tens of thousands of years. I don't know. So these are kind of some old quotes. There's a guy, Metrodontus, even before Aristarchus, about 100 years before the guy who figured out, parallax, told us we were at least a light year away from the nearest star. And all they had was no telescopic observations, no computers. They basically had like sheer force of thinking, and they would make these arguments like, how weird would it be if you went into a field and there was a single blade of wheat? That'd be pretty weird, right? So I think there are other stars with planets out there. It's not very scientifically rigorous, but that's what you had. Then Giordano Bruno, of course, he said the space was infinite and that around every star there was a Earth-like planet, and this is what got him burned at the stake, actually. The thing he said was that the Earth-like planets also had an Adam and Eve on it. So around every star there was like a copy of Earth with their own, so exciting that they all got to share the joy of original sin and be tortured and expelled from Eden. So that was such a terrible idea. Whoops. But we named a crater after him, so everything's good. So realize that you luxuriate in the scientifically literate 21st century. And what these people literally gave their lives to, think or reason about, we now know this. And now we can start asking the frivolous sci-fi questions about what types of planets are there? How do we get there? What are their fun-loving inhabitants like? Is it this, or are they sentient balls of energy that want to share ever-loving kindness with us? Like, what's going on? So we're almost here. Probably, I would have been pushing you guys to pay attention to gravity waves up until still do it. But I think the next huge thing to fall in your lifetimes maybe takes 10 years or something like that. I don't think it would take too much longer. The meager trickle of science funding continues to eke out. Is that somebody will say, we found life around another planet. Now, it won't be like a phone call. It'll be like an abundance of oxygen that wouldn't be explained by natural processes. Or there's a great article that came out in Science or Nature a few years ago that said, does ET use hairspray? Claiming that maybe what you should look for is aerosols and pollutants. So the way that we ripped a hole in the ozone layer, so they would have been able to see that. But we've seen this. Now the question is how. So, and to appreciate the technical issue is, again, grapefruit model. This is the sun. It's the size of a grapefruit in the scaled down model. Closest star to us is a tangerine in New York. And in the grapefruit model, if you're even giving yourself the luxury of looking for Jupiter, that's the size of a marble, and it's not emitting power through thermonuclear fusion, hundreds of tons, thousands of tons every second. So how are you going to see this marble in New York? What hope do you possibly have of seeing this marble in New York? How could you see it? In fact, because anybody see the planet in this picture? And this is our backyard, right? Yeah, you guys are staring at Mercury for 30 seconds without realizing it's there. So it's a hard problem. And the answer to the hard problem does a lot of other things. So the first idea is to use gravity. And what you're used to thinking about at this point is the planet is being tugged around in orbit by the star, right? So the planet experiences a very big force of gravity. It's curvature of space-time now, but force of gravity is good enough. What is the planet doing to the star? The thing that we can see very readily, and the thing that we could keep track of is, let's say this thing has a huge force on it of 10 to the 50th newtons or something like that. What's true about the force that the star experiences? Yeah, equal and opposite. So says Newton's third law. So why is the planet being whipped around in orbit while the star is basically stationary? Well, it's just because the star has much more mass than the planet. But the planet is putting a force on the star, and it's a big force. So while the star makes the planet whip around in orbit, the planet actually makes the star wobble a little bit. We're actually making planet Earth, all of planet Earth, us included, you're doing your little part, is making the sun orbit, like wobble back and forth by a couple of centimeters per second. It's like this fast. Okay. So how on earth are we ever going to see that? And it took pretty heroic efforts, but the trick is this, is you're not going to see the thing wobble left and right and left and right and left and right, but there are these very delicate features in the stellar spectrum, and what you can do is you can see the very delicate features in the spectrum wobble towards and away, towards and away. And the trick is through Doppler shift. So Doppler shift is this thing that you're probably most familiar with in sound, right? So cars driving towards you, you hear kind of a high-pitched noise, and then as it goes away from you, what is it that you hear? Yeah, I would do it, but I'm too dignified to. It's not true, actually. So I'll just do this. Doppler shift. And that's a big Doppler shift because sound only goes at like 350 meters per second. So when you're driving at, about 30 meters per second, you're moving at 10% of the speed of sound. So you have this 10% ish change in pitch. Light is a wave. So light does this too. This is a generic phenomena for all wave phenomena. So this is what Doppler shift would look like. Let's move this away. And let me see if we can increase this a bit. There we go. So we have a source, and then we have an observer, and then I'm going to start the source emitting pulses of sound or light. It doesn't make a difference. So one, you can see the effect of the finite speed of travel of light and sound is that the source was emitting stuff. It took a while for the observer to observe the stuff. So this is just two things out in the cosmos. One's emitting light, the other one's absorbing light. But now what's going to happen when I put one in motion? Let's make it go towards the observer. What do you think is going to happen? So what it gets is the wave information. So what it'll start seeing is exactly that. So the waves don't increase in speed, but the frequency will go up, because the thing is running into its own waves, basically. And then as it passes, this is basically the chirp. This is the... Okay. So that's Doppler shift. And it's basically, if it's coming towards you, it's running after its own waves. If it's running away from you, it's running away from its own waves. So you would see this, the speed up and the slow down, or increase in frequency, decrease in frequency, even though the speed of light isn't changing, speed of sound. So light does this too. Why don't you notice this with light? Who's ever, argued your way out of a ticket by claiming I was going so fast the red light looked green? Can't do this? No. Well, you could, I guess, but you would be admitting that you were moving at like half the speed of light, which would be pretty hard. So this is an exaggeration, but imagine that there was, a light on this train as well as the sound, is that the light coming here would have a shorter frequency because the train was running towards the waves that it was emitting, and the light coming away from the train as it was going away from you, the wavelength would be stretched out because it was running away from its waves. Right? So imagine a light bulb and it's moving really fast this way. The frequency of the light would be compressed, shorter wavelength, and here the frequency would be longer. This guy's freaking out. I don't know who makes these pictures. Okay, so light does this. The reason we don't notice it on an everyday basis is because you would need to be traveling at a fraction of the speed of light. But as you guys know from week 1, is things do move very fast in the cosmos. So we give these things names, even though it might not necessarily be blue light that we're talking about, or red light, or whatever. Is we talk about, stationary source would be unshifted. This is what it should be emitting. The eye and the boomy thing are not moving relative to each other. If the star or orange explosion is moving towards you, the wavelength gets shorter because it's running into its own waves, and the frequency goes up. Because blue light has shorter wavelengths and bigger frequencies than red light, we call this blue shifted. It's the act of compressing what would otherwise be a longer wavelength wave. Even though this could totally be a red laser. It just means the wavelength is shorter because it's walking towards you as it's doing this. So same idea. If it's running away from you, we call it red shifted, even though, again, you can have blue shift. You can have blue shifted red light, red shifted blue light. It just means it's shifted towards the blue or towards the red. So towards you, away from you. Yeah. It would. Yep. It would affect the, not in practice, because to literally make, well, that's not true. At the edge of the cosmos, so the cosmological redshift will make things that would have been red and white look infrared. But in practice, especially for close things and things that we'll talk about, you don't detect an overall change in color necessarily, because we're not talking about things moving at a fraction of the speed of light. What we're going to hope to do is, at least in the context of exoplanets, is look for a couple of meters per second, right? Because that's really what you get from the planet's influence on the star. Okay. Then questions about Doppler shift and somewhat annoying but fairly reasonable terminology? Okay. So how are you going to use this? So now imagine that this is actually a star and it's actually being tugged around by a little planet that you have no hope of seeing. Are you going to literally look at the star and say like, oh yeah, it looks a little bluer today. Oh no, it looks a little bit redder today. That's not going to be very helpful. In fact, if a star starts looking, looks a little bit blue or red, you would just assume it's on a different part of the main sequence, right? So we assign color to temperature and not necessarily to speed. So there's no help there. Is there something about star spectra that might be helpful, though? Is something that should be pinned to a physics or a chemistry textbook and we should know about? Yeah, so the excellent suggestion in there is, and now you're thinking like a real astronomer, is if you're baffled by something, you should just say, I need to take the spectra. So what is it in the spectra that, could correspond to something that you might see in a laboratory? It's not like the overall shape of it, but within a spectra, you have what? They're features of spectra that are very finely etched, and we know what they should be based on, physics or observation. There are lamps here. Yeah, those thingies. Yeah, so again, take spectra. It's the one, if you're stumped as an astronomer, it's like take spectra. And when you take a spectra, these are a little bit cartoonified, but let's say I gave you these three spectra. And they're the same overall type of star, right? But you see this set of spectral lines in one star, and this set of spectral lines in another star, and this set of spectral lines in a third star. And it looks like this spectral line, the shape and the distribution of them, they kind of correlate. I have 2, 1, 3, 2, 1, right? So what's true about these versus those is that these, and now we kind of see why these names exist, is more towards... Exactly. So these are more towards the red, and these are more towards the blue than I would see in the laboratory, is kind of how you might imagine it. But I should know what these are. Like if I know that this is a hydrogen line, I could I could suck it up and go talk to a chemist and say, what's the hydrogen line supposed to be? And they would say 656.285 nanometers. And you can get this out to, six significant figures. That's pretty good. So I'd have, part in a million or something like that. And what's true about this star versus this star? So this one is doing what? Towards or away? Frequency going, away. Good. Redshift is away. And then this one is blue shifted. People get excited when things are blue shifted. It's like, it's coming towards us. Everything else is running away. So blue shifted, it's coming towards us because the wavelength has been compressed. And this is a cartoon. Just remember the features that you guys saw and you circled things on them. They're these very finely etched, very sharp dips. And you could know this in principle from laboratory measurements to very high precision. So you look at this, and this is a real spectrum, and this is a real terrible out-of-whack picture where this comically oversized telescope is looking at the star that seems to be wobbling by a tremendous amount. If it's coming towards us, the spectral lines will be blue shifted. If it's going away from us, the spectral lines will be red shifted. If you sit there looking at a stellar spectrum and you see one of these lines wobbling back and forth once every month, what do you know is happening? Yeah, something's pulling it around through gravity. And if you don't see like a binary companion or anything, the star is just sitting there wobbling by itself, well, the thing that's making it wobble just can't be seen. Probably, you got to rule out that it's a very, very faint companion star, but it could be a planet. I don't know, I should animate this, but you would see one of these things. These very finely etched transitions just wiggle back and forth. And very periodic, Like if it was a sun-like planet and a sun-like star and an Earth-like planet orbiting it at 1 AU, you would expect this to wobble back and forth once every year. If it was Mercury, once every 38 days or whatever it is. And so finally, people kind of detected lumps of stuff around neutron stars really weirdly in the late 1980s. But the real first, this is a true planet around a true star, 51 Peg B, which means we ran out of Greek letters and you got into the 51st brightest star in the constellation Pegasus. So it's really not anything exciting. And if you looked at the wavelengths and saw them rock back and forth, this is meters per second. This thing is being pulled basically plus 80 meters per second, minus 80 meters per second, up, down, up, down, up, down. Looks like a nice uniform curve swaying back and forth. What's causing this star that's not in a binary system to be rocking back and forth over the course of a couple of weeks? It must be an exoplanet. So the people who did this, they built this comically oversized spectrograph. So what you guys did is you took these little filters and put them in the goofy laser viewers and looked at these lines and you're like, that's pretty cool. Imagine something about half the size of this room. That was their spectrograph. And there are all these technical problems where they went in to fix something and then they turned the lights on. And every time they turned the lights on in the room, went fix something, and then left and sealed the room again, the problems always got worse. So you're literally confronted with this issue where no matter what you try to do, you always make it worse over months and months. And what they found out is that the old storeroom where they were taking the spectra, there was really mildly fluorescent paint on the walls. So every time they would go into the spectrograph room, turn on the lights would basically charge up the walls with the fluorescent paint, and for a week afterwards it would slightly irradiate their detector and they would get crap signal. So very frustrating. But eventually they won, and it was actually really impressive. Now we kind of do it, people kind of do it as a matter of course, but the first Doppler shift measurements, those people might even call them fanatics. So what kind of planets do you think this technique works for? Now that you know that it's the force of gravity that's causing it, and you know so much about how to make the force of gravity and the acceleration due to gravity big. So we're talking about the acceleration of the star. This is the thing that we're seeing. G you can't change. How do I make A as big as possible? So whose mass is that? Is it the mass of the star? It's the planet's mass. So what kind of planet would we need to have rocking the star back and forth? Very massive planet. And how do we make the acceleration big? So the numerator has got to be what? 1 over, it was in denominator, so you want it to be, to make A big, you want it to be teeny tiny. So what kind of planets do you think people saw at first? And this is an artistic depiction thereof, is people kind of, I don't know what they were thinking, but they were called hot Jupiters. Yeah, because they were very close and they were very warm, and they were very massive. And they're a little bit perplexing because you would imagine that if you took our Jupiter and moved it to half the distance from the sun as Mercury is, the sun would just blow off all the outer layers of Jupiter and really quickly kill the planet. So the first things that were discovered are just these really baffling objects, actually. This is very old. You can tell it looks very 90s. Picture of the first hard-won handful of planets around other stars. And these are in terms of Jupiter masses. And this is our solar system for scale. So this is the 51 Peg thing. It's about 47% of Jupiter's mass. It's about a quarter of the distance as Mercury is. This one, actually, it wobbles really far back and forth, but this called the Virgo massive planet is about 6 times the mass of Jupiter and still about the distance as Mercury. So these are really weird things at first, but these are the first set of data. So getting much better, get down to a meter per second or something like that. So that's about the speed of somebody on a skateboard. So savor that for a moment. Is 50 light years away, we're seeing these planets wobble back and forth by the speed of, basically a brisk walking pace through the Doppler shift. But the important part, as well as the first set of exoplanets, people are again really excited about that, is that Doppler shift is going to be useful for much more than exoplanets. Doppler shift is going to be our key to cosmology, because it turns out galaxies, and this will be so much easier, galaxies are also moving, and they're moving much faster than this kind of walking pace of planets in our local neighborhood. So the next thing that people were able to do is multi-planet systems by finding this actually kind of weirdly complicated looking wobble of a star, and it turns out it wasn't one planet, it was a whole bunch, and you could pick them apart. And the technique to do that is the same thing that your ear does naturally. If you're like listening to music, you know what instrument is. So you're actually implicitly doing a Fourier series inside your head. But you can pick this apart, and it turns out that here's something that's about 2 times Earth's mass. That's pretty good. It orbits once every 3 days, so that's very fast. So it's got to be really close. Maybe 15 times Earth's mass. It's got a speed of 10 meters per second, where that's the speed that the planet's being pulled around. It orbits once every 5 days. So these are still really, really close things. But people are getting better, and it was, again, the first success. So we'll stop here for questions, and the one that really gets us to thousands and thousands of planets, and doing this as like, exoplanet detection factory instead of fighting really hard for each one individually, will be the idea of transits. So we'll pick up with that on Wednesday. But any questions about Doppler shift? Yeah. Yeah, so the theories behind the hot Jupiters, what we do know, unless there's something really wacky out there, is that the mass of the planet basically tells you what it must be composed of. So you cannot make something that's 10 times the mass of Jupiter completely out of rock. Right? It just doesn't work. So they are gas giants. If you get down to about Neptune's mass, you could be a water world or something like that, or you could be a very gassy thing with a hydrogen envelope. So in between the terrestrial and Jovian planets, there's some kind of slippage room, but these must be gas giants. So how is this gas giant surviving so close to the sun? The trick that might do it is the atmosphere is the part that is in trouble. So how do we protect our atmosphere, in particular on Earth? So we have something that Mars doesn't. So Mars lost its magnetosphere, but we still have one. And Jovian planets have a pretty big magnetosphere, so there might be some weird, symbiotic, helpful envelope of really strong magnetic fields that's keeping the solar wind from the star, from blowing this thing apart. The other option is that, there are trillions, hundreds of billions to trillions of planets in the Milky Way galaxy, and we might be seeing ones that are really just destined to be eaten. And something happened to this thing, and now it's on this death spiral coming in, and it's going to be eaten by the sun, so its star. So that's also a possibility. So maybe these things are just being sucked in, and we see them just before they get eaten by their suns. Because there's also something about these solar systems that's a little bit funny. Is you would expect them all to be orbiting in the same direction, right? You'd expect the star to be rotating clockwise, for instance, and then all the planets to be orbiting the star clockwise. And for these things, 50% of them are orbiting in the wrong direction, and it's this sign of trauma, basically. It just doesn't seem right. It doesn't agree with our pretty well accepted theory of solar system formation. So maybe something hit this, and now it's on a collision course with the star or something like that. I don't know. Depends how lucky or unlucky you are. So if somebody just stopped Earth in its tracks and let it go, we wouldn't have a very long time, a couple of months before we were eaten by the sun. If you're spiraling in really slowly in an unstable orbit with gas drag or something like that, then who knows? But it could be. It could be millions or something. But that's the blink of an eye in cosmic time. But there's some indication that these are, now that we've opened up the transit pipeline and all of this data is coming out, these are not typical. They were just the first things that we saw. Yeah, I think the trauma theory behind these would be that they formed farther out, and then something happened, whether it be like gas drag or a collision or something like that, is just slowly pulling it towards the center, and eventually it's going to be eaten. And we see it like right before it happens. Cosmic time. Yeah, so it turns out you can pull a lot of information out of some of this information. Doppler shift is one of the least useful techniques to get information. If you look at a transit curve, which is what we'll do later, is this technique is actually like very useful because stuff like how symmetric are these things, how sharp is the drop, what does the bottom look like, is there something on the other side when it actually transits around the backside. You can pull out a lot of information about rotation and atmospheres potentially from that. But Doppler shift, in a weird way, isn't very helpful. So this is what you get. How much stuff can you pull out of this set of really scruffy data points? You can fit a cosine to it, and that's basically what you get. So, yeah, the transit stuff, there's a lot of information in there, but Doppler shift, I don't know. To imagine that there's more info hiding in there than you can see is, it's kind of hard. So this is, you should be happy with this. It's the speed of a skateboard, But yeah, it would be nice to know things like the tilt, the composition of the atmosphere, and whether or not they're co-rotating and stuff. But with this technique, I don't think it's very likely. This, however, we'll get to on Wednesday. Awesome. Other questions? Okay. So why don't we take a 5-minute break so I can pull this stuff down. I'll meet you guys downstairs at